Sunday, August 14th, 1 week before the totality. And this is what the traffic looks like this is Highway 26. We're out of the town of Mitchell on the way to John Day.
We're in the John Day National Monument fossil bed area, taking Highway 19 towards the town of Kimberly. We're heading on a path that'll take us north, and at some point we will transect the center line of the eclipse activity that's coming up next week. That'll be the part of the eclipse pathway that'll have the longest period of totality, and in this region it's expected to last about 2 minutes. But as you go further east, it'll last a bit longer.
Okay, so Jeff and I pull off the road to come here to the John Day fossil beds, and we met this charming family from Taiwan.
Yes.
You came all the way to America to see the
Eclipse.
the eclipse, the totality, as we say.
Yes, total solar eclipse. And we have seen our first eclipse in Libya,
In Libya,
Sahara Desert, at 2006.
2006.
Yeah, but they have not been
born yet.
Yeah, so
That
this
was
is the
my
first
guess.
time for them to see the eclipse here.
So are you excited to see the eclipse? Yes.
Great.
They're practicing their English. And your name is
Kiwi Lin.
Kiwi Ling,
Yes.
and this is
Bronto Wu.
well, welcome to Oregon.
Your
可以
name?
介绍一下 Introduce yourself.
What's your name?
My name is Alan Wu. My name is Brian Wu.
Oh, Brian.
They are twins.
Oh, twins. Wow. Nice to meet you.
Nice to meet you.
So, you said you brought your own telescope with you?
Yes. So we have 4 big luggage here. Oh, thank you very much.
So, are you camping or staying in a hotel?
We are camping at the Solar Fest in Marches. Yeah.
Oh, in Madras.
Yeah,
And-
so
oh, in
they will
Madras.
set up the tents for us.
Oh my God.
Yeah.
How long did you have to book in advance?
I booked that in February this year.
February.
Yeah, maybe 6 months ago.
So you're what they call solar eclipse enthusiasts.
Enthusiast. oh yes. We like this astronomy, spatial things.
Oh.
Yeah, we teach earth science
Oh, you teach
in
earth
Taiwan high
science.
school. Yeah.
So you and your husband are both teachers.
Yes, we are classmates in the university.
It's all
So this is the
Annular eclipse. We took the picture in Tunisia in 2005. Yeah, that's different from this one, total solar eclipse, because the distance of moon and earth are different. So the annular would be when the moon is much far than normal. Yeah, and the total solar eclipse is when the moon is much near the Earth. Yes. Thank you.
Too bad you can't bring your whole class here.
Thank you. And welcome to Taiwan in 2020. We have an annular eclipse too. Yes.
Oh, well, we'll hope to see you there.
Okay, thank you.
Jeff and I just left the town of Kimberly. We're on our way to Monument. And we came across a rustic campsite. Do you see it's not full yet? Although there are a few campers. We came down to cool off in the John Day River. So I noticed from your license plate, you're from California. Yes, we are. And you came a week early to see the
Sure, we had a
eclipse.
spot.
To make sure you had a spot. Is this your first eclipse or
No, it's our second eclipse.
second?
And we're meeting our kids and grandkids who experienced the first eclipse with us down in Mexico, and they're meeting us here to watch another one and pass on the excitement.
Well, lucky kids. So here's another camper and
What's the name of this camp?
Lone Pine Park.
It's pretty rustic, isn't it?
Yeah, it's nice.
and we see you're another Californian.
Yeah,
Where
yeah.
Did you come up from Santa Cruz?
I'm in Pacifica, just south of San
Oh,
Francisco.
sure, Pacifica.
But I was I came through here in June scoping this place, scoping places out, and I have this photo project where I photograph the sun, and I've been doing that for about 10 years, and I needed a spot that had a nice eastern view with a big mountain, so I want to include the landscape. And that was actually a tall order. It was harder than I thought.
But you did it.
Yeah, and so I wasn't sure. I'm sure you guys probably feel a little bit the same about how insane this was supposed to be, you know,
I
with
know.
traffic. And I'm like, do I need to be here 2 weeks ahead of time?
We haven't seen it yet. We
Yeah,
haven't seen the traffic yet, but we've heard a lot of talk.
yeah. I mean, I have to say, so
what is this
and
now?
I printed this thing out on I think it was NASA's website,
Could be.
Total,
where you could
Total
get this.
Solar Eclipse.
And they had
Over
Idaho and the whole,
Sure.
all the way to South Carolina.
So the red lines are where?
The path.
That's the 60 or 70 mile wide path, and then that center
Town
line.
of Lincoln is right on the center, and that's where I thought it was. And it looks like if you hold it perfectly level, you can see it's drifting southeast. There's a line that goes southeast, and you'll notice on this little chart, what is it, about a minute and 45-second duration here? What is it here, do you know?
I can't need my glasses.
Anyway, so the duration increases as you go along this
Yeah.
until you get all the way to the southeast. I think it's
Somewhere like in
South
Tennessee
Carolina.
is
Tennessee, right?
is where it gets the longest. It's
Yeah.
like 2 or 2.5 minutes or something.
We just heard from these folks over here. They went to Baja for a total one, and they had it for 5 minutes.
I know, is that insane?
That's insane.
That would have been awesome, just to be in Baja too.
So here we are in the Malheur National Forest. Jeff and I pulled over, and this kind, sweet lady stopped, and I know she has a license plate from Washington State.
Yes, I'm from College Place, Walla Walla area, and I'm down here looking for a spot for the eclipse. I have a mom who's 91 years old. Her name is Elora Ford.
And your name is?
I'm Mary Lou Ford Steinweg. And my mother is just really looking forward to seeing the eclipse. So
that
I'm
is so
looking
cool.
to see if I can find a place so we can all watch. She and her 3 children and a few other family members. There'll be 6 of us.
What kind of accommodations will you be having?
Well, actually, we have the privilege of staying in the fellowship hall of the Seventh-day Adventist Church.
I'm happy to say Jeff and I finally found the perfect spot. We're about 5,800 feet up in the Malheur National Forest. I would also like to point out the clear blue skies. So that will mean no clouds, hopefully, for the totality. In this part of the state, it's usually pretty rare to have cloudy. I'm in the town of John Day, which happens to be on the path. I came in to do some shopping early. Stopped here at this coffee house.
My name is Heather Rookstool, and I'm the manager at Java Jungle and Tropical Tan.
On the main road
It's 142 East Main, right on Main Street
in John Day.
in John Day, Oregon.
Hello. So, you were telling me that how many people are expected into this town. And what's the population of John Day right now?
John Day has 1,700 people, and we're expecting to have 50,000 in Grant County. Grant County has 8,000 people in it. The things that we're going to be close to running out of is gas, ice, and probably milk at the grocery store.
And you said you've already met people from other parts of the world?
Yes, I had a couple in here from the Netherlands and then another couple from France. Grant County is a low-income community. I mean, it has less jobs, so we survive in the summertime on tourists. So maybe if we do a good job showing them how cool we are, then maybe they'll come back and visit again or tell their friends.
I just noticed this sign here. Welcome visitors, Eclipse glasses only, $1.
This is what the sun looks like through the solar filter glasses that are provided for eclipse watchers.
We're biding our time. We have 5 days. I get to hear Jeff play his music. With so much time on our hands, we find ways to entertain ourselves. And here, you see we have our solar panel. Oh, Jeff here is playing
A version of Upwards, using an Upwards board. And basically I'm doing it in Spanish.
Here is the moon, exactly 10 a.m., August 16th. As you see, it's a thinning crescent. It's about 60 degrees from the sun.
Vanessa's checking our messages on the phone because we're expecting an astronomy friend we call El Marco to join us here on our hilltop. Not only for the solar eclipse, but he'll be bringing along a telescope, and we will be doing a lot of night sky astronomy. So Vanessa, what are you doing to keep yourself entertained?
Well, I picked up this book in town in a little free box. It's called The True Believer by Eric Hoffer.
It's an extraordinarily beautiful day here on day -5. We are making ourselves quite comfortable. Most importantly, we are going to have the generosity of the sun keep us well charged so that we can go about our various activities. Vanessa is continuing her vocal studies. We did a video back 2014 where she was learning how to sing. I've noticed over time her intonation has gotten better and better. Hey Vanessa, I see we're playing another game here with the Upwards board. What game is this going to be?
This game is called Forwards. It's something that actually you made up.
Oh, I should know the rules then. How does it play? How do you work?
Well, you pick 7 letters, and out of those 7 letters that you picked, you have to make a minimum 4-letter word.
That's the 4 in forwards.
Forwards, yes. So Jeff, I understand that the total eclipse is about the moon passing in front of the sun. Is there anything else you'd like to add?
That's pretty much it, but there's a lot behind it. Anyway, I was just playing a song called Solar by Miles Davis. There's your own father, John Ruddy, now passed on, had a wonderful philosophy of life, and it was that everything is in motion. Think about that. Everything is in motion. Wherever there's motion, events occur. The incredible thing about solar eclipses and everything else is that the motions are incredibly complicated, but at the same time quite predictable. Astronomers, for instance, for millennia, thousands of years going back to China, have been able to predict solar eclipses in advance. The main reason being that as far as the ancients were concerned, and even some folks today, events occurring in the heavens have a tremendous influence on our day-to-day lives. Interestingly enough, solar eclipses by the moon were considered to be very baleful, dire events, predicting that something very awful was about to happen in most those societies.
Oh, and today it's just
Well, there have been events, but I don't think I've seen anything as cataclysmic as you might expect from such kind of a prediction about eclipses. But in a moment, I'll give you a few ideas about how the celestial mechanics works in terms of the motions of the heavenly bodies.
so here we are, biding our time playing word games.
I'm going to play this one. It's called Outwards, all by myself. But usually we play together, and if we play together, we win together or we lose together. What's nice about playing with someone else is then you have two sets of words to choose from to put down.
Two sets of letters.
Problem is sometimes they have collisions between the players. But when you play all by yourself, then you're the one who screws up. In this game, I can only make words along the outside, and one of the words has to be an 8-letter word and go all the way across. Modern societies approach events like this almost as though they're festivals. Whereas in the past, there was the beating of drums. For instance, the Chinese believed a huge dragon was swallowing the sun, and they were afraid it wasn't going to emerge again. So modern societies have a much more positive viewpoint towards things like comets streaking across the sky. They're no longer portents of dire warnings about events. Solar eclipses, lunar eclipses, novas appearing out of the heavens, stars that did not exist, seem to exist before, suddenly flashing into the heavens, being brighter than the planet Venus. All those things were dire because the ancients used to think the sky was the foundation of stability of the cosmos. And when anything weird, out of turn, or unexpected occurred, they thought things were going to hell in some kind of a handbasket.
I can see that, anything unexpected.
This is the third game that we play on the Upwards board. It also involves 7 letters. In this game, you cannot put a letter on the perimeter at all. All the words have to be on the inside. And the bottom line is you have to use, like the other games, you have to use every letter or you lose. But in this case, you can make short letters, words, 2-letter words, even 1-letter words if you want to play a word. The problem is we have yet to win a version of this game. It is so demanding. Modern attitudes towards strange celestial or unexpected celestial phenomena began to change with the Enlightenment. This was about 1780s when people started looking around and saying, you know, nature isn't as magical and as unpredictable as we think, but all we have to start doing is paying attention to events, and we'll be able to illustrate or underscore certain cosmic themes, laws, and principles that can explain all the things that are occurring in the heavens. For instance, now we know that novas are not exactly what they sound like, new stars. They're actually stars that are at the end of their cycles of lives, and they blow off their outer shroud of atmosphere and sometimes can glow as brightly as an entire galaxy. But astronomers fundamentally understand that now, whereas in the past it was all superstition.
Was there one astronomer who discovered something that...
Well, in terms of novas, I'm not familiar with a particular astronomer who made a study of that, but there has been...
No, I mean as far as the eclipses not being dangerous events.
Well, astronomers have been tracking the planets, what they call the wanderers or planets, for a very, very long time. And when it started to become pretty clear that some of the events could be predicted, even among the Chinese, they started to get a handle on it. They started saying, well, you know, if we can predict something's about to happen, maybe it isn't as auspicious as we thought. Maybe there's just some kind of giant cosmic clock in motion and events are all sequenced to that. So as soon as they started to be able to mathematically predict the regularities of the cycles of the moving bodies of our own solar system, they were able to begin to offset the fact that dire warnings were portended in the heavens. Now, another thing, however, they couldn't predict oftentimes was comets. Comets would just flash out of the Oort cloud, which is this huge mass of matter orbiting really far out in our solar system. And they would just come, some of them would just come in once and disappear. So since they could no longer predict comets at that time, weren't able to do it at the time or see them in advance, still comets held on for several centuries, all the way up into the time of the Enlightenment, as indicators of portents.
On top of all these activities, Jeff practices keyboards. We have a very entertaining life.
Now, as soon as the Enlightenment came around, and for instance, Newton noticed that things irrevocably fell, like the falling of the apple when he said this universal law of gravitation. And Newton had the first insights into motions of bodies in space. Remember, your own father's notion of motion is the essential aspect, quality of the entire universe. Things are in motion, people are in motions, nations are in motions. Motion is everywhere. As soon as Newton came up with this notion of gravity as being a universal feature or natural law, they began to be able to predict the orbits of things a little better. So no longer was it simply a matter of, well, we've got these numbers that always seem to work out as a pattern, and we can always find Jupiter where we expect it to find it, or we can find the moon passing in front of the sun on a regular basis, predicting its location and where its shadow would fall. They suddenly had a notion of actually how it all worked. And how it all worked is the universal law of gravitation causes all motion to be bent in space, in the sense that gravity deflects things from their normal paths. But once gravitational systems are set up, those paths become very regular and predictable mathematically. So Newton's insight into the universal law of gravitation gave way to what we would call classical celestial mechanics, which is the motions of bodies in space based on gravitational influences and mass. So Vanessa, it looks like you finished your game of Inwards.
Yes.
And I noticed you have a number of letters
Yes,
left. What does that mean?
I lost by 5 points. Because you cannot go around the circle. And this is another one of the games that we made up for, as in the words of dear Einstein, that imagination is more important than knowledge.
So we didn't have to get the box and tell us how to play this game or make it up. We made it up for ourselves.
Right.
Of course, the original Upwards may be more fun, but it's always a lot of fun when you figure something out for yourself. So what do you think you're going to do in the future to maybe use a few more of the letters? Did you learn anything from it?
You just never know what, it's unpredictable every time because you have to draw letters out of the bag.
Well, notice this is a
I
letter.
did see that.
Lo is a biblical word. Ox, right?
Oh, that I didn't see.
And let's see, is there anything else? Z.
La and do, re, mi, fa, sol, la, and axe.
Okay, so now really you've only got two letters left. And it also proves that no one of us is smarter as all of us. In the time of Newton, there was a belief that there was an ether that permeated all of space, and that this ether was responsible for the propagation of light waves through the celestial medium, in the same way that water propagates waves across the surface of the ocean. So waves occur in water because there is a disturbance or a stress that occurs in the water which upsets the water and the waves begin to propagate. And they noticed that in many ways the way light propagates and moves through space is exactly like that. So they believed in a thing called the ether, permeating all of space through which waves of light and other things could pass and were propagated. Well, there was an experiment in the 1880s by a couple of scientists named Michelson and Morley. I don't know their first names, but basically the Michelson-Morley experiment demonstrated that light just moves through space as a vacuum and it had nothing to do with an ether, and they did this by doing an astronomical calculation experiment based on Jupiter and the light from Jupiter across several different axes. And they said, okay, there's no such thing as an ether. So we got rid of the ether, but that introduced a serious problem for all of celestial mechanics, because now there was no surface or ocean surface that you could rely on in order to determine where something was located related to something else. In other words, there was no absolute reference plane for anything in the universe. Everything was subject to the perception of the observer. Vanessa and I are about to head off on a hike. Probably not through the woods in this case. Personally, I believe there is something akin to the ether, but it's not like water. I think that there is a certain non-vacuum to space in which astronomers are now beginning to understand, and they start to see it in terms of things like dark matter and dark energy. There is something substanding space that is not exactly like water. It's something that defies the Michelson-Morley experiment slit experiment where they deflected light along different paths and it came back together again as they expected without a vacuum. But the fact is that this particular ether is not something we've really discovered, but we do see evidence of. And I'll give you an example, tadpole faces. Go online and look up tadpole faces. Faces appear on that look like frogs on the faces of tadpoles during Kirlian photography, which suggests that the face is already there and it's drawing together all the proteins and cells to create the frog. And we might consider that to be an etheric phenomenon.
I wonder what these are.
Another instance in which there's something like the ethers is the fact that astronomy predicts the Big Bang, but all the galaxies and stars and everything in the universe should be distributed uniformly in space. In reality, it's not distributed uniformly. And by uniformly, I mean something like this. If you swing the camera around, you're going to see a bunch of rocks. Swing the camera on the ground around us in the clay. Those rocks are randomly distributed. They're not uniformly distributed. If they were uniformly distributed, you see like a pattern in all the rocks that just went on and on and on and on, like stepping stones or something. Well, the galaxies and stars and everything else are very similar, particularly the galaxies. So astronomy has no way of accounting for the fact that galaxies have there's an order to it, but at the same time that order isn't uniform as they might expect based on a Big Bang. So this is another instance of some kind of force exists in the universe that gives shape to everything we see around us.
Views beyond the tree line are pretty rare up here. You can see off in the distance there is a mountain peak and a series.
There's snow on it.
The initial solution to the problem of celestial mechanics and the fact that there was no absolute reference frame in space came out of this obscure Swiss patent officer, Albert Einstein, in 1905. And what happened was he said we don't have to have an absolute reference frame and that all events in time and space are relative to everything else, so that something that looks like something to me, a light particle moving through space that looks blue could look red to someone else. Somebody further away would see it in a different position from somebody closer, on and on. Everything relates to the observer, where you stand at the time of measurement, at the time of looking at something. Now, what this meant for him was that space and time were bound together, and he called it the space-time curvature. Mass, for instance, causes space to curve, and that's why bodies move not in a straight line through space, but they move in curves. Well, the importance of understanding curves is that that's exactly what's going on now. The moon is curving around the Earth, and at some point its curved path is going to intersect with a curving path of the Earth around the sun. And when those two things occur, we're going to see a transit. And we're going to see that in this particular instance, the moon is so close to the Earth, because it has an eccentric orbit, that it's actually going to blot out the sun, even though the sun in summertime is further away from the Earth in the northern hemisphere at this time of year.
And how rare is this event?
I think, I haven't made a particular study of eclipses, but I'd say every couple of years there's one somewhere on the planet. Now remember, the planet's 8,000 miles in diameter, and the shadow from the moon is probably where it's actually darkest and covering the moon. It's probably only it's only on the Earth about 100 miles. That's why we're here now, because the shadow that falls on the Earth is only about 100 miles wide, even though the moon is some 2,500 miles in diameter. So that shadow can only fall on a small part of the Earth, and the place where it falls is generally always different, although there's a certain regularity to it.
We've arrived at a deep, dark, thick wood.
Going back to Albert Einstein, there's something really incredible about solar eclipses. There was no proof for Einstein's theory of relativity. And then somebody realized that, hey, if light actually is shaped by gravity, then the stars should be slightly out of position during a total eclipse. So I think they went to somewhere in South Africa, a bunch of astronomers, and they set up telescopes and they measured the positions of the stars relative to each other and relative to the sun,
its position, and they found out, yes indeed, light from distant stars, where it comes from, does not line up in a straight line when it goes around the sun. The sun has enough mass and enough gravity to literally curve like a lens, light coming from distant stars. And that was one of the first verifiable proofs of Albert Einstein's notion of the space-time continuum and the fact that gravity actually warps space, light, and the motion of not only just the motion of objects, but also the light that passes through the space-time continuum. We've now encountered fencing. Typically this is a border of a national forest beyond which ranchers in this area of the country go about the business of raising cattle. Oftentimes, of course, their cattle are allowed to spill over onto the national forest land, hopefully most of the time by license, but occasionally by taking license. The validation of Einstein's theory of relativity that occurred with gravity warping light actually occurred in a total eclipse in 1919. And here we are, 98 years later, we're sitting here in this wide open expanse, and we don't really need to be here, frankly, because you can see the eclipse anywhere along its path as long as you can get out from under the trees and it's not overcast. We're here at this spot because, frankly, myself and another friend, El Marco, who is on his way as we speak, are amateur astronomers, so what we want to do is set up a telescope, and we are going to be looking at the night sky, but we will manage somehow to get up at 10 o'clock in the morning on Monday, the 21st of August 2017, just to have a nice look at the transit, or rather prosaic transit of the moon across the face of the sun. Look at this magnificent creature. I have no idea what it is. It's a bird. Could be a vulture. It likes to glide. Beautiful, beautiful.
Today's day -4, as we see the crescent moon is thinning and getting closer to the sun. It's about 50 degrees off now. And our friend El Marco has finally arrived, and we are about to go on a hike.
Vanessa and El Marco are intrigued by the butterflies, or what we call flutterbys, that we're finding on these thistle plants along the roadway. I have a question for you, O Jefe. Can you please explain the Saros cycles?
Saros cycle.
Saros. You know how eclipses run in cycles? Just had a question from El Marco about Saros cycles. Saros. How does that spell?
Saros. S-A-R-O-S.
S-A-R-O-S.
Saros.
That doesn't sound like a technical term to me. It sounds like someone's name. But basically we agreed that it meant that eclipses come in clusters and cycles. There's long periods where they don't occur, and then there's shorter periods where you get a number of them. For instance, there'll be one in 2020 in Taiwan. That's the prediction. Now, my question for El Marco is, why would eclipses come in cycles of more and then less? What do you think is the principal reason for that, astronomically?
It's symmetrical alignment of the Earth and the Moon
in terms of their orbits, yeah. Because as we know about the moon has what is called an elliptical orbit. It's not a perfect circle. In fact, it varies by about 20,000 miles. So it goes out to about 245,000 miles away from the Earth, and in about 225. Now that's probably what explains the differences between a total eclipse and a what kind of eclipse, because it goes in and out in terms of distance. Annular eclipse. So when the moon's further out, it can't cover the whole sun. Now the reality is that the ellipticity of the Earth's orbit only really determines the difference between an annular and a complete total eclipse of the sun. The Saros cycle probably has more to do with the fact that the moon's orbit is tilted at an angle to the Earth's orbit around the sun. So only every once in a while does the orbit of the moon coincide with the orbit of the Earth around the sun in order to result in an actual eclipse of the sun by the moon. So I think it's really incredibly amazing coincidence that the Earth, that the moon and the sun's relative distance produces a total eclipse for us. That is just a cosmic coincidence of the most epic proportion. Yeah, it is interesting because the sun, at its distance of 93 million miles, is about a half of a degree in size, what's called 30 arc minutes by us astronomers, right? And the moon, at the point where it's in proximity closest to the Earth, is also about half a degree or 30 arc minutes in size. And it's just like your fingernail, just covering it. But keep in mind that the distance between these things is like much further than I can possibly ever reach between the sun and the moon. In my reading about astronomy, both solar system and outside our system, I've heard of this thing called Bailey beads.
Bailey's beads, yeah.
Bailey's beads. Do you know what those are? Bailey's beads are a phenomena where the moon is just about to completely eclipse the sun, but you're seeing some of the sun rays shoot through mountains of the moon.
Right.
Yeah,
I can understand
these little diamond points, like on the side of the eclipsed sun. The reality of anything in space is nothing is a perfect circle. Nothing. Our sun isn't a perfect circle. Our moon isn't a perfect circle. The topology of the moon is such as you have craters that are indentations on the limb of the moon, and you have mountains on the limb of the moon. So what we're going to see during the eclipse is, as the moon just covers it, you're going to see little bright flashing lights around the outside at different points. That's the Bailey beads. That's great. I didn't know what that was called. Something very interesting from a book I read recently, that the sun's corona is not symmetrical, and it's dependent on where the sun is in its sunspot cycle. So I believe for this August 2017 eclipse, the corona is going to have a sort of a perpendicular, that's not the right thing, but a more rectangular shape, and it'll be oriented at an angle like this. It won't be a complete circle. It'll be sort of shooting sideways. Well, as we know, sunspots are basically regions of the sun that are cooler, and it largely occurs because the magnetic field intensity at certain locations on what is called the chromosphere of the sun, the part that we see with our eyes, varies. So it gets cooler in spots and hotter in spots, and the coolness is caused by the magnetic intensities of various tremendous toroidal storms of magnetism and its interaction with the sun's surface that creates these darkened spots, which affects the entire distribution of light upon the surface of the sun. Okay. One of the things we just mentioned about the sun, we've actually mentioned several things. This thing called the corona. We mentioned a thing called the chromosphere. The Earth, like the Earth, the sun has many different layers. The outermost layer of the sun, strangely enough, goes all the way out throughout our entire solar system. Do you remember the name for that part of the sun that goes out way, way far? Solar winds? Where the solar winds come to an end. There's a special name for it. So the sun actually extends in its influence. Heliosphere. Heliopause is where it ends. So our sun actually has an influence that goes out, I think it's almost like a trillion miles out into space. I think we'll head out there, by the way. Let's head out there. We've already hiked this road. In fact, the heliopause is now being transcended by humanity. You know how it is? Do you know what I'm referring to, El Marco?
Turning into the menopause?
No! We've got 4 probes of our solar system that are now approximating to the heliopause, where the heliosphere of the sun ends. The influence of the sun is gone. They're entering into what is called the interstellar media, the ISM. Now, those probes are the 2 Pioneer missions and the 2 Voyager missions. And of course, everybody knows Voyager because it was in the first Star Trek movie. Coming inward from the heliosphere, collapsing way, 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 way down, is what we called the corona earlier. And that's about 3 million miles across. So if you put your fingers up and you cover the sun with one finger, and then you take the other 2 fingers flanking it, That's about the size of the corona that we'll see during the totality on Monday. One of the greatest mysteries about the sun is the corona. And the weird thing is that the surface of the sun is about the same temperature as the core of the earth, about 6,000 degrees Fahrenheit. But the corona itself is several million, at least 1 million degrees in temperature Fahrenheit. An extraordinary thing that astronomers have yet to explain, and physicists, astrophysicists. My working theory is that there's some quivering going on in the magnetic sphere of the sun.
It's afraid, something like that. It's quivering.
Quivering. It's like afraid. I'm going to lose these photons. They're going off into space. No. So it's quivering, and that excitation of a small oscillation in the magnetic sphere of the Earth, of the sun, sorry, causes the ionized particles in the coronosphere to get really, really excited in a way that we can't really explain at this point in terms of physics. So we now know that there's this thing called the atmosphere, sort of the sun, called the corona. But there's another layer down, and El Marco's going to explain that and give the terminology.
I think the visible part of the sun's surface is the photosphere, hence the name photosphere. I'm not sure, but maybe there's an outer layer around the photosphere called the chromosphere, and that might be where you can see these violet or magenta prominences shoot off the sun if you're at sufficient magnification.
Now we astronomers have a way of seeing this, even though it's not a totality.
Correct.
What kind of I think it's a kind of filter, right?
Right. There's a hydrogen alpha
filter.
Wavelength filter that you can use, and that allows you to see the prominences shooting off the sun.
And the way the filter works is it excludes every other color of light except for a very narrow range of light that allows us to see these events occurring, these prominences, this ejecta, these coronal mass ejections, and all kinds of other things. It's a fairly expensive filter, but I recommend anybody who's got a small telescope consider getting one.
And so it excites, what is it showing? Excited ions in the hydrogen alpha?
In the hydrogen alpha band.
Something like that?
Well, looks like we've come to the end of this road. It's probably private land on the other side by a
cattle rancher, maybe?
Cattle rancher.
This discussion, pretty much. I might continue on up. Really? Okay. Yeah. You should do. Okay, so we're now going to talk about the inside of the sun, the part we can't see. And we can do it from the inside out or the outside in, but since we've already covered the chromosphere and the photosphere, the next layer down is very thick. It's called the mantle, and it's very similar to our own Earth, which has a mantle. It's a large, expansive area where nothing's going on other than these huge, how would you describe them? Convection currents. Yeah. And they cycle heat out and in and out and in. It's one of the reasons why the sun has such a variable magnetic sphere, because hot stuff comes up, boils up, and then gets cool and sinks back down. And this is happening all throughout the sun, like a giant flower with petals that are going in and out. That's the mantle. Okay, now, not being conversant in everything about the sun, and we're kind of doing this on the fly, inside the mantle is where it's all really happening in the sun. It's the place where nucleosynthesis occurs. The sun is like this athanor, it's like this furnace where it's transforming very simple atoms of hydrogen, which exist in terms of a single nuclear proton, generally, and a single electron. Well, by the time we get there, that electron's been split away. All that's left at the reactive core of the sun are nuclei of hydrogen atoms, and those atoms are vibrating with such force, and they're compressed together with such effort that they actually fuse, just like that, creating helium atoms. And we'll explain how the energy is released in a moment. Okay, the really fascinating thing about why energy is released during nucleosynthesis is the mass of two protons together, which is a helium nucleus, is mysteriously lighter than two separate hydrogen atoms. So if you actually weighed two separate hydrogen atoms, they would weigh more than if you take a helium nucleus of an atom. Two protons that have been forced together are lighter than the two hydrogen nuclei, which is the protons. So two protons weigh more than two protons separate. And that difference in energy is what shoots out
of the nuclear skin at the core of the sun, and then it starts burning its way up through the mantle, causing all this heat to be generated, these huge convective cells, and every time it encounters an atom, what happens is it loses a little energy. So it starts off as, do you remember the names of those rays? There's cosmic rays, and then there's another
Gamma rays.
Gamma rays. Whenever two nuclei fuse of a hydrogen atom, it releases gamma rays. And those gamma rays then begin the process of shooting up, and it takes 20,000 years for those gamma ray photons to finally shoot off the surface of the sun, but they don't leave as
absorbed and
re-emitted, absorbed and re-emitted. Right. And then when they go out, they're a much weaker form of energy, which we call light.
So I have a question for the lovely camera person. There's a formula that describes the energy emitted during nuclear fusion. Can you recall what that formula is?
Oh, the one from our great friend Einstein. E = mc squared.
That's right, yeah, rock and roll. To action. So, Hefe, I heard you use the term photons, and to me that sounds like it would be visible light only, but is that true? Is it only visible light?
No, actually it is not just visible light. There are many different layers of photons, and the only thing that varies among them is the rate at which they vibrate, oscillation. So in the olden days when they first discovered these things with like radios, they knew that the oscillation frequency of photons was very long, like this. All right. Before that, of course, we could see light, and we knew it oscillated at a higher rate. Now, what they eventually discovered when they developed sensors for it is this thing called infrared radiation, which is in between visible light and radio waves, and that oscillates in an intermediate frequency.
The amplitude of the waveform.
In fact, there is a wavelength that goes all the way through our entire universe, and it's a leftover vibration from the Big Bang. It's called the cosmic microwave background radiation. And microwaves are just above regular radio waves in their rate of oscillation. But now there are oscillations that are above visible light. First one is called UV.
Right, ultraviolet.
Then the next one's called X-rays. And then the next one's called gamma rays. And then beyond that, there is a thing called cosmic rays that are so powerful that one of the reasons we can't travel healthily through space is gamma rays will go through just about anything. And if they go through lead, they'll actually be slowed down to the point where they can be destructive because they become X-rays.
And cause genetic damage to humans, yeah.
By the way,
it's not amplitude, it's frequency of the wave that I was talking about. Amplitude is the height.
That's right. We want to clarify
frequency.
That. That's why I said the vibratory rate. That's correct. Okay. So we'll go on. We'll think about it.
You didn't mention neutrinos yet.
Okay. Now, I'm a little thirsty. We pass this around.
No surprise there.
Inside here is a thing called H2O. Hydrogen, 2 hydrogens and 1 oxygen. Hydrogen dioxide. That hydrogen, by the way, was here from the very beginning of the universe, but the oxygen wasn't.
That's true.
Where did that oxygen come from?
That comes from the stars, from being fused together in the core of stars.
So there are stars that are far more massive than our sun. Our sun's about 1 million miles in diameter, but it's fairly diaphanous. There are stars that are much smaller but far more dense. And they go through an end life cycle that is such that when they finally use up all their hydrogen, and they have enough mass to use up their helium and their carbon, they can explode. And when they explode, the pressures and temperatures are so high that it results in oxygen. And then the oxygen
and every other thing,
every other
gold,
which astronomers,
every other heavy metal,
which astronomers call metals. Everything beyond hydrogen, helium, and lithium, I believe, is a metal to an astronomer, even though it's not like this. Yeah. So at the end of a star's life cycle, when it explodes and it creates all these heavy metals, other weird stuff happens. In fact, when a star of any significant mass turns into what we call a
white dwarf,
or I'm talking about its final stages, a nova, right? When it turns into a nova, something really mysterious happens. Even space and time itself is oscillated. What do we call that?
Space-time oscillation?
Yeah, called a gravity wave. And you know what? 3 or 4 years ago,
the LIGO experiment, which was using extremely sensitive laser beams over long distances, detected for the first time a gravity wave being propagated through space.
I think gravity waves they detected, was it rotating, two black holes rotating each other?
Until they finally coalesced.
That's
exactly
the
right.
thing that kicked out the gravity waves, I think.
Because the sensitivity of the thing is not good enough yet for novas. Actually, that's very good. Yeah, you're absolutely right. So we talked about how stars can create all the matter that's in the universe, which we call astronomical metals, right? And that there were primordial atoms like hydrogen, helium, and a little bit of lithium, maybe some beryllium, I don't know. Now the thing, and we talked about the fact that when stars end their lives, they create all these other things like iron, even up to uranium, right?
Everything heavier than your basic
I think carbon is as much as is normally created by stars.
I'm not sure, yeah.
So we've also talked about the fact that two stars, like a couple of black holes cycling in on themselves, can create gravity waves, but there's other mysterious things that are emitted too. They're called neutrinos and antineutrinos. The antineutrinos are emitted by all stars when the hydrogen nuclei combine to form helium nuclei. And then neutrinos are shot out at the same time as the gamma rays that shoot out from the combination. Now, I don't know about neutrinos, but they're supposed to be very mysterious. They move at the speed of light or maybe even faster. And they go through phase shifts and everything else. And there's some kind of experiment you mentioned.
Yeah, so something about neutrinos, they're very, very difficult to detect. Something like this, there's billions of neutrinos passing through us all the time.
Wow.
But they don't interact with ordinary matter very often. So they built these gigantic tanks down in Antarctica, sheltered from all other forms of radiation, such that the only thing that'll cause an effect on these tanks are neutrinos. So they'll see these flashes, these long streaks of flashes, very rarely when a neutrino happens to interact with ordinary matter in these tanks in Antarctica.
Because we're pushing. But getting back to eclipses, it's a very interesting thing. For instance, the period of totality for this eclipse is going to run what, El Marco?
Well, in our location, about 2 minutes. And in general, about 2 minutes across.
But I understand that by the time it gets to Tennessee, it's supposed to last maybe twice as long.
Okay.
And the reason for that is this. The lunar shadow is like a cone. It goes like a cone, like an ice cream cone. It goes to a taper. Well, our eclipse is going to happen at 10 in the morning, which means we're a couple thousand miles further away from that cone than Tennessee, where it's going to happen at midday, which means it'll be since the Earth is rotating, it'll be closer to the moon, which means the swath of the totality will be larger, and the period in which the totality will be seen by any viewer in Tennessee, for instance, will be longer. So that's why they'll probably have as much as 4 or 5 minutes of totality compared to the 2 minutes we're going to get here.
I have a related...
Oh, so why is it that these totalities or eclipse occur on different places on the planet, not the same place?
You want to shoot
each
for that?
time?
Go ahead. Okay. Well, basically, the Earth is not lined up at its equator directly with the sun. So here's the sun, here's the Earth. If the Earth was perfectly rotated around its axis, and that axis pointed directly at the sun all the time, yeah, they would pretty much fall in the same places. It would always fall at the equator. But the reality is, the Earth has a tilt to it, like this, and that's why we have a Tropic of Cancer and Capricorn.
That's why we have seasons.
And meanwhile, the moon is also presenting at slightly different points at the time of the eclipse too. So its shadow, the cone, goes off at different angles. So that's the two main reasons why you don't see an eclipse happening here every 5 years, for instance, or 10 or 20 years, according to the Saros cycle that you mentioned earlier.
Today's day -4, as we see the crescent moon is thinning and getting closer to the sun. It's about 50 degrees off now.
Hey, Al Marco, what are we about right now?
We are about to move a telescope from an SUV.
Wow, that's great. Now, how did you come about selecting this site, pretty much?
I didn't. It was done by someone else who told me to do it.
Well, what are some of the things we're looking for?
Well, for a good astro site, it's very hard to get a great astro site. You want dry conditions, out of the wind, great horizons in all directions, an open sky, but you also need shade trees nearby so you can camp in the morning and not broil out in the broiling sun.
So let's see. We want to.
And privacy. You need privacy.
Privacy.
Can't have crowds all around you, screaming kids and barking dogs at 6:30 in the morning after you stayed up all night long.
So how late will you be observing to tonight?
I will probably observe till 4 a.m. tonight.
Now I usually knock off about 2, don't I?
Yeah, on a good night.
On a good night.
When you really try hard.
Go. So what are we looking for here?
Well, we've tried to select a site that optimized as many of those criteria, those factors that I mentioned earlier.
Now I know when we observe in the past, you have to go and do an extensive alignment of the telescope so that it'll point where we want it to point.
Right.
What are some of the things you look for under those conditions?
Well, basically, with this kind of telescope system, which has a pointing computer in it, you have to tell the pointing computer where various points are in the sky, so it knows where everything is.
I think we spend a lot of time making sure we get a good view of the North Star, Polaris.
Yeah, that's a good one. That's an easy star to align on because it doesn't move in the northern hemisphere.
And if I sweep up to the sky, and right now, folks will see that the North is right behind. Polaris should be visible right between the crowns of those two trees up there.
So yeah, we're looking directly south here, and we've got a decent southerly horizon. There's a bunch of small trees off in the distance which will block our view. It's not superb because we're on a downslope here, and there's a little hill kind of rise in front of us, but it's pretty darn good.
And we've tried to stay as far back from those southern trees as possible in this location.
That's true, yeah.
Now what about the other directions, like let's say up to the south?
That's east.
And east. This is the southeast I'm just pointing towards here.
Yeah, southeast is okay. East, we've got a big tree blocking us. We're a medium-sized tree anyway, so we're not going to get stuff in the.
But
in the
overhead, obviously,
overhead looks very good.
Very good. Yeah. And then to the south.
We talked about that.
West.
To the west. Yep. Southwest,
that's pretty good.
We've got one tree there, but it's okay. It's not bad.
And our altitude, I think, was 5,900 feet, something like
about that. Yeah,
and the beauty of altitude is that the sky gets thinner and thinner. And
right. You're looking through less atmosphere, which dims and blocks the stars and also makes them more blurry. All right, so this site we've chosen here, which is also in the 2017 eclipse totality path, happens to be a black site as far as this Clear Sky Clocks astronomer's website goes, which means it's very, very dark here. There's no artificial light pollution, so the Milky Way galaxy and all the dim objects that we search for will just look fantastic. There's no big cities around, and there's no very bright point sources of light like prisons or large industrial facilities which would have a superb amount of lighting.
Now I understand you're the president of the Santa Cruz chapter of the Dark Sky
current
Association?
chapter leader of the Santa Cruz chapter of the International Dark Sky Association. Okay. Yes, and that's our mission, is to educate people to use appropriate lighting. We're not against all lighting at night because you need some lighting for security purposes. We're just against excessive lighting or inappropriate lighting. So what you want to do is you want to shield your lights. You want to, if you can, use warm spectrum lighting, blue lighting, and not use excessive amounts of lighting either. So shielding, not too bright lights, and if you can, warmer spectrum lighting. So not blue LEDs, but say 2700K warmer
something
color
in the
temperature.
orange and reddish colors.
2700K color temperature, less than 4000K.
Now I notice the sun's starting to get down, so hey, I know we both need time to set the scope up and everything else, so we're going to sign off.
Arrivederci.